Hi guys, sound check.
Hello. Before we start, may I ask you a few questions about the upcoming control work?
Yep.
So will it be proctored, like using Zoom or Examus or whatever else?
Yep.
Um,
We will use Examus.
Examus?
Yep.
Was
Are there
it?
any problem with that?
Yeah, we had a really bad experience with Examus when we had our mock exam on English. Around 65 people out of 89 had bad technical problems with it, including not being able to open the task, etc., etc. I can send you the whole list. We gathered some statistics, and we heard about really bad experience that other teachers had with it. So
Okay, so is it possible to avoid using Examus and stick to any other alternatives?
Well, I know that on the upcoming control works on the calculus, we will use Zoom, and on other faculties like on PMI, they also use Zoom. It depends on the control elements.
Okay, I see. Okay, I know about this issue with the Examus. And actually, currently I'm thinking about avoiding this system. I still have time to make a decision. Okay. So if you also had a bad experience using Examus, then it's probably a good idea to avoid using the system.
Yeah, it would be really nice.
Okay. Okay, let's do this.
Okay.
This Wednesday, I'll have a long session, like visiting hours or consultation for you.
Okay, yeah.
It happens since 6 p.m. till 9 p.m. I don't know, do you already know about this or no?
Well, I've seen like in the table schedule.
Oh, okay, okay, so you're already aware of this. So let's discuss this problem during this consultation.
Okay, yeah,
well,
sure.
I know how to organize the control work without using Examus. So if we have these issues, then it's probably better to avoid the system and we will use Zoom.
Yeah, it would be really nice. Okay.
But I have to, how to say, I need to think about how to organize this using Zoom. And I have to think about several details that are not clear to me right now. So let's discuss this on Wednesday, and, and we will take the final decision.
Yeah, and one more question then. Will we have a demo variant?
Okay, there is no zero version because everything you encounter during the control work is, well, you will find in the homework. Like all these problem sheets on the wiki page, they contain everything you need to know in order to solve the test. So just go through all these problems and you will be fine.
Okay, thank you.
No problem.
Can I ask a question?
Yep.
Is it enough to go through the homework problems, or it's
again? Could you repeat?
Is it enough to go through the homework problems, or would you also recommend to go through the seminar problems?
Well, they are more or less equivalent to each other. So if you go through the homework problems, it's more or less enough. But, well, it's always better to look through all of them. I mean, it doesn't hurt, at least.
Okay.
Okay. I think we should start. Just give me a second. Okay, so let me recall where we are, and then I will explain what we're going to do today. So now we're currently discussing polynomials in several variables, and we discuss the analogy of the Euclidean division algorithm, which is called reduction. And so let me recall the details. Okay, so we have a field F, and we consider the ring of polynomials in n variables, and we fix some lexicographical order on the monomials of this ring. Well, this lexicographical order depends on the ordering of the variables. So by default, I assume that x1 is greater than x2, etc. But you may choose any ordering on the variables you like. Then there is a procedure called reduction. So if you take a polynomial f, you can reduce it with respect to another polynomial g. This is called an elementary reduction. This is an analogy of one step of the division algorithm. And just in case, do I need to remind you how this reduction works? Are there any problems with this? Okay, so then what I want to discuss today, well, the first thing, I didn't prove that the division process halts. That is, if you take a set G of non-zero polynomials, then we defined this process, which is called, this is an elementary reduction, and this is a reduction process. And the reduction process consists of several steps. You just take a polynomial from the set G and make one step of reduction. Then take another polynomial from the set G and make another reduction, and so on. And the problem is why this process halts. So does it stop after refinitely many steps? So, and the answer is yes, this process stops. And this is the first thing I would like to prove for today. After that, I want to switch to Buchberger criterion. This is a criterion for a set to be a Gröbner basis. And after that, I will discuss applications of this criterion to several problems. And during the next lecture, I will prove the Buchberger criterion. Okay, so that was a quick reminder. Now, let me formulate a brief lemma. But before doing that, let me recall that each polynomial can be presented in a form like this. I should use a different letter, where Ci are coefficients and Mi are monomials. And I write them in a strictly decreasing order. So M1 is the highest possible monomial, then M2 is the next highest possible monomial, etc. And I introduced special names for these guys. So M1 is called M1 of F, then M2, let me write it here like that, M2 plus, etc. So then M2 is called M capital 2 of F, etc. So M capital I of S means the ith largest monomial in the polynomial, if it exists. So I will use this notation during the next lemma. So the claim. So as usual, we have a field, we have this ring of polynomials, and we have a fixed lexicographical order. Now, suppose that F prime and G are polynomials such that F prime is an elementary reduction of F with respect to G. And suppose that M1 of F equals M1 of F prime, etc. M (k-1) of f equals (m)(k-1) of f prime. So the first k-1 highest monomials are the same. And suppose that there exists mk of f and there exists mk of f prime. Then, so the claim, then mk of f is not smaller than mk of f prime. So if you reduce a polynomial f to a polynomial f prime and they have the same leading monomials up to number k-1, and they both have the kth monomial, then the kth monomial of the initial polynomial is not smaller than the kth monomial of the reduction. So this is an auxiliary statement. So let me show you how to prove this. So suppose, again, f is given in this form. Plus etc. plus CR MR. And f prime is a reduction of f. So, well, let me recall you how the reduction works. When I do a reduction, I take a monomial in the polynomial f, and I replace this monomial by the sum of strictly smaller ones. And this sum depends on the tail of g. So precisely, I multiply a tail of g by some monomial and then replace this one by the tail multiplied by a monomial. So let's see what happens here. So we know that the first leading monomials of the polynomial f prime up to the level k-1 are exactly the same as in f. So the monomials appearing here are exactly the same as here. So if I did my reduction with f, then I didn't touch all these monomials, because if I made a reduction with, of any monomial here, then it disappears. But the leading monomials are exactly the same. So the beginning of f prime is exactly the same as the beginning of the polynomial f. And then we have two options. Either the reduction was for the term for the monomial mk, or the reduction was done for some smaller monomial. Well, if the reduction was done for a smaller monomial, then, so this is the case number one, the reduction was done for the smaller monomial. Then we have this monomial untouched, and here we have something smaller. So in this case, this guy is mk of f prime, and this guy is mk of f. And we see that they are the same, and this corresponds to the case where we have equality here. Now, suppose the second case. The reduction was done for the monomial mk. Okay, in this case, the monomial mk was replaced by a sum of smaller monomials. So in this case, f prime looks like this: c1 m1 plus ck-1 mk-1 plus, and here we have something, some monomial, let's say c prime m prime plus etc., where m prime is strictly smaller than the monomial k. So m prime is strictly smaller than the monomial mk. And this will be mk of f prime. And because mk is mk of f, then this is exactly what we want. So in this case, we have a strict inequality here. So everything here is just by definition. So are there any questions regarding the proof? Okay, I hope it's clear. So now we're ready to prove that the reduction process halts. So the claim. Again, F is the field. We have this ring of polynomials in several variables and some lexicographical order. Now, for any F and for any F here, for any F here, and for any subset here without of non-zero polynomials, the process of elementary reductions halts, where Gi from G, this process halts. So after finitely many steps, we will get a polynomial which is not reducible with respect to any polynomial from G. Okay, so how to prove this? Well, suppose this is wrong. Suppose the contrary holds and we have an infinite sequence of reductions. So then we can write the monomials of the initial polynomial f, like C1, M1 plus etc. CK, MK. Then F1 will be something like, let's say C1, 1, M1. I will write an index of the polynomial f, F1, here on the top. So for the polynomial fk, the index will be here. So this is not a power, this is just an index in order to distinguish all the indexes. Yeah, k was a bad choice here. Let me use a different letter. Let's say t, the number t. So I pass by a reduction process from one polynomial to another polynomial, etc. Now let's look at the first monomial in each polynomial. So by the previous case, applying to k equals 1, we see that the leading monomial of each polynomial in this sequence is not increasing. On the previous lecture, we proved that every strictly decreasing sequence of monomials halts. So in the sense, after some point, you will encounter exactly the same monomial. So by the previous lecture, there exists a number, let's say R1, such that all the leading monomials, oh, I'm sorry, here it must be 1. All the leading monomials for the polynomials from the step R1 are exactly the same. So this simply means that all these leading, so from some point here, all these leading parts are exactly the same. Okay, so then we will look at our sequence starting from this point and below. And we have a sequence of polynomials having exactly the same leading monomial. Then we look at the second highest possible monomial. Yeah, and by the way, let me denote this leading monomial by M1 without any index. M1 star. Okay, then from this point, if I take a look at this polynomial, we have this plus some monomial on the second place, Then we have its reduction R1 plus 1, which looks like this. Etc. So all these guys are the same. And by the previous lemma, these guys are in this relation. So M2 on the step R1 is not smaller than M2 on the step R1 plus 1, and so on. So again, after finitely many steps, we will find some number R2 such that here the monomial on this, the second monomial will be exactly the same for all subsequent polynomials. So again, we will find like this. So here M2 star will be exactly the same. Well, and we know that M1 star is strictly larger than M2 star. Well, we can proceed in a similar way considering the third monomial. It stabilizes at the monomial M3 star. Then, since we have an infinite sequence, we will never stop. We can continue this process. So at the end, we will produce a sequence of monomials like this, and this will be an infinite sequence. Infinite decreasing sequence, strictly decreasing sequence of monomials. And this contradicts to the result of the previous lecture. So this is a contradiction. And this contradiction completes the proof. So let me show you the whole proof again. So we look at the first monomial. The first monomials must decrease. Then they stabilize at some monomial M1 star. Then we look at the second monomial. It stabilizes at some monomial M2 star, etc. And all these monomials will give us an infinite descending chain, strictly descending chain of monomials, and this contradicts to the results from the previous lecture. This is how we prove that the reduction process holds. Are there any questions? Should I repeat something, or is it clear? Okay, that's good. So now I want to switch to the Buchberger criterion. So let me recall the definition of the Grobner basis, just in case. Grobner basis. So we have the, so if we have, as before, all of this stuff like polynomials and elliptic graphical order, and we have a polynomial f, and we have a set of non-zero polynomials. So now, after this result, we know that we can produce a sequence of elementary reductions with respect to G, and after finitely many steps, we will get a polynomial such that we cannot proceed. So this polynomial cannot be reduced by any polynomial of G. So here we have like G1, G2, etc., Gk. And the process holds here. But then we may use a different sequence of reductions with different number of steps, and we may get a different polynomial. Yeah, by the way, these polynomials are called reminders. And it may happen that these two reminders are different. So this may happen. So this means that the division process is not well defined. The reminder could be different. And by the way, in this case, we will write this notation. So this notation means that we reduce f to R1 using a sequence of elementary reductions with respect to elements of G capital. Okay, so the Grobner basis. So the definition of the Grobner basis is simple. So it's a set of polynomials such that the remainder is well defined. So for every polynomial f, all possible reductions lead to exactly the same remainder each time. So the remainder doesn't depend on the choice of these sequences of reductions. So now we want to determine if a set a Grobner basis or not. So how to check? For example, I give you a set of polynomials. How to check if a polynomial, or if this set a Grobner basis or not? And there is a really cool criterion. It's invented by Buchberger. Actually, Grobner bases were invented by Buchberger too, and he named them after his advisor, Grobner. Okay, but before formulating the criterion, I need one additional definition. So suppose we have two polynomials, G1 and G2. And again, we have a fixed lexicographical order. So everything here depends on the choice of the order. So we may present the polynomial G1 in the form C1 M1 plus G prime 1. And here, this is the leading term of the polynomial G1, and G1 prime is the tail. G2 is C2 M2 plus G prime 2. And again, this is the leading term of the polynomial G2, and G2 prime is the tail. Then we may consider the least common multiple of the monomials M1 and M2. So the least common multiple of the monomials M1 and M2. So this will be some monomial we denoted by M. And since this is a least common multiple, it's divisible by M1, so it can be presented in the form T1 M1, where T1 is also a monomial, and it can be presented as a T2 times M2, where T2 is also some monomial. And now I want to multiply this polynomial and this polynomial by some specific monomials, and then cancel the leading terms. So I do it like this. The S polynomial of G1 and G2 is the polynomial of this form, C2 T1 G1 minus C1 T2 G2. So I multiply G1 by a monomial and a coefficient. I multiply G2 by a monomial and a coefficient, and then subtract the second one from the first one. And after this operation, I cancel the leading terms. Let me demonstrate this. So if I compute this explicitly, C2 T1, here C1 M1 plus G1 prime minus C1 T2, C2 M2 plus G prime 2. And now, if you open the brackets, you'll see that T1 times M1 and T2 times M2 gives you the same monomial M. So this will be M. And then we have exactly the same coefficient, C1 times C2 in both cases. So we cancel these summands here. And the result will be C2 T1 G1 prime minus C1 T2 G2 prime. So this polynomial is called the S polynomial of G1 and G2. So this is S polynomial of G1 and G2. And the miracle is everything we need to know is hidden here behind these S polynomials. So S polynomials know if a set a Grobner basis or not. And let me formulate the criteria. The claim. Okay. Oh, by the way, before formulating the criterion, I forgot to give you an example of an S polynomial. So let me show you an example. I think it's a good idea to pretend at least one example. Let's say we have the polynomial ring over rational numbers, and the lexicographical order with respect to this ordering of variables, and the polynomial g1 is xy minus 1, the polynomial g2 is yz minus 1, then the leading terms here are xy and yz. The least common multiple of xy and yz is xyz. So this guy is T1 and this guy is T2. The coefficients C1 and C2 are equal to 1, so we don't bother with them. So the S polynomial of G1 and G2 is equal to Z times xy minus 1 minus x times yz minus 1, and the result will be x minus z. So this is the S polynomial of G1 and G2. Okay, so now I'm ready to formulate the Buchberger criterion. I'm not going to prove it now. I will prove it on the next lecture. But today I want to discuss its corollaries. So the claim, the Buchberger criterion. Okay, suppose we have a field. I just want to formulate all the context here because there are a lot of stuff you have to remember, so it's easier if I recall everything explicitly. So we have a field, we have a polynomial ring over this field, and we fix some lexicographical order. And now G is a set of non-zero polynomials. Then the following two conditions are equivalent. The following are equivalent. The first condition, G is the Grobner basis. And the second condition, for every pair of polynomials from the set G, their S polynomial can be reduced to 0. This means that there is at least one possible reduction. So there exists a reduction. So you don't have to check all possible reductions. You need to check that there is at least one reduction to 0. And this is a criterion. So you can always use this criterion to check if a set a Grobner basis or not. So again, just go through all pairs of polynomials in G, compute their S polynomial, start reducing it to 0 in any way you like. And if you get 0 for all pairs, this is a Grobner basis. If for some pair you get a reduction which is not 0 and you cannot reduce it further, then this is not a Grobner basis. Well, for example, in the case here, if we compute this S polynomial for G1 and G2 and get this guy, we see that this guy is not reducible with respect to any of these ones. So you cannot reduce it with respect to G1 and you cannot reduce it with respect to G2 because there are monomials of degree 1, of total degree 1, and no one of them is divisible by the leading terms of G1 and G2. So you cannot reduce this guy to 0. So the set consisting of G1 and G2 is not a Grobner basis. That's it. You see how easy to check this condition. Okay. Now, are there any questions regarding this criterion? Okay. So now let me formulate one additional statement. So if you want to check this, you usually want to know some tricks. There are several tricks allowing you to simplify the computations. Well, it may happen sometimes that the S polynomial automatically reduces to 0. So let me formulate one such trick. Let me show you. So suppose, so a remark, it's not obvious. This won't be obvious, and I will not prove the remark. But just in case you know that this is not obvious. But this is a very powerful remark. So if you have this polynomial G1 and G2, well, suppose that the leading monomials are coprime. So suppose that the greatest common divisor of M1 and M2 is 1. Then S polynomial of G1 and G2 reduces to 0 with respect to G1 and G2 automatically. So if you have two polynomials with coprime leading monomials, then you don't need to check this reduction. It will be 0 automatically. So you always can reduce it to 0. So for example, if you consider something like this, in the polynomial ring x, y, z, you take this order and you take something like x squared y minus, say, minus z and something z squared plus 1, then the leading monomial here is x squared y and the leading monomial here is z squared. And we see that they are coprime, so the S polynomial of these guys automatically reduces to 0, and hence this set is a Grobner basis. So this is a Grobner basis. This is how it helps. So usually you don't have such a pretty situation. Usually you have something like 2/3 of all S polynomials you have to reduce to 0, and like 1/3 of S polynomials is automatically reducible to 0 via this remark. So, but it's useful. Okay, now I want to switch to the ring of reminders. So we discussed the ring of reminders, or the quotient ring, in the case of polynomials in one variable. Now I want to define exactly the same ring here in the case of polynomials in several variables. But before doing that, I need to present some terminology related to ideals. So we have this ring of polynomials, and suppose we have a finite set of polynomials G1, Gk here. Then we define an ideal, the ideal generated by G1, Gk as the set of polynomials of the form G1 times H1 plus etc. plus Gk times Hk, where H1 and Hk are all possible polynomials from the ring of polynomials. So I define this set to be this guy. So this is just the set of all possible linear combinations of G1, Gk, but the coefficients here are polynomials. And this is an ideal. So this is an ideal. And we call this ideal the ideal generated by G1, Gk. So this is an ideal, and we call it the ideal generated by G1, Gk. Also, if you denote the set of all these polynomials by G capital, we can write this, we can use this notation. So this is exactly the same thing. So just a simpler version when you want to shorten the notation. Okay, well, it happens that every ideal here in this polynomial ring can be presented in this form. It's called the Hilbert-Basis theorem. I'm not going to prove it. I just want to use it. And actually, I will not use it in any.
Can you please repeat what you said? Just what is it?
Oh, okay. Yeah. Let me.
Generated by one
the
or
claim the Hilbert-Basis theorem. Basis theorem. The Hilbert-Basis theorem says that every ideal in this, here F is a field, every ideal of this polynomial ring can be, for every ideal there exists a finite set of polynomials such that this ideal is equal to the ideal generated by these polynomials. So in case of one variable, we know that each ideal is generated by exactly one polynomial. But here, every ideal is generated by a finite family of polynomials. And this is what the Hilbert-Basis theorem states. And the amount of the number of these polynomials could be larger than the number of the variables, and it could be smaller. So there is no relation between n and k in general. Okay. So yeah, let me see how much time do I have and how much stuff I would like to cover. Okay, so now well, let me explain the philosophy of what's going to happen. Well, when we deal with polynomials, usually we can solve a lot of problems using ideals. So if you have, for example, a problem, let's say you want to solve a system of polynomial equations, or you want to do something else, or you can find equations defining a curve on a plane or something like that. You can always reformulate this problem in terms of ideals. Always. This is the strength and the power of the algebra. Every problem can be reformulated in terms of ideals. So if you want to find a really cool tool to solve all possible problems about polynomials, you have to find a cool tool solving problems about ideals. So now, I want to deal with ideals in an effective manner. So how do I do this? So for example, so now I know that each ideal is given by a finite set of polynomials. So if someone comes to you and gives you an ideal, he probably gives you a finite family of polynomials. So, but now if you want to deal with this ideal effectively, well, you need to change this initial set of generators by a good set of generators. And this simply means that you want to replace the set G1, Gk by a Grobner basis, such that this Grobner basis also generates the ideal I. So the problem, the first problem we want to solve is we want to, let's say, we denote this set G1, Gk by G capital. Now we fix some lexicographical order on monomials. Because before this point, we didn't have any order. Because if you want to define an ideal, you just define a finite family of polynomials. You don't need to specify the order on the monomials. But now, when you want to deal with this ideal in an effective manner, you have to specify some lexicographical order, and after that, you have a notion of a Grobner basis. Because before you fix some order, there is no notion of Grobner basis at all. You cannot define a Grobner basis without choosing an order. You cannot define a reduction without choosing an order, etc., etc. So everything we discussed before was highly dependent on the choice of the order. So here we have to fix the order. So well, this is the crucial point. So everything here will be dependent on the choice of this order. And now we want to replace this set by a different set, let's say G0, such that the ideal I is also generated by the set G0, and the second condition, G0 is a Grobner basis. So this is the first problem we want to solve. So we want to replace the set of initial generators by a Grobner basis. And this can be done using the Buchberger algorithm. So let me describe the Buchberger algorithm. So the context. So we have a field, a ring of polynomials, and some lexicographical order. An input. We have a finite family of polynomials. So what do we want to find? The output. We want to find a set G0 which contains the initial set G, such that it's also finite. So such that G0 is also finite. It's a Grobner basis, and it generates the same ideal as the set G. So we want to extend the initial set to a Grobner basis. And this is what the algorithm does. It solves this problem. You eat a finite set of polynomials and you spit out a finite Grobner basis defining exactly the same ideal. And this procedure depends on the choice of the lexicographical order. So now let me describe the algorithm itself, how it works. The algorithm. I don't want to be very formal. I just want to explain how it works. So you start with the initial set G, and you consider all possible polynomials from G, and you compute the corresponding S polynomial for each pair Gi, Tj. And then you reduce this S polynomial with respect to G and get the remainder Rij. So for each pair of elements here, you just compute S polynomial and then reduce it with respect to the set G. Now, if all these guys are 0, then G itself is a Grobner basis and the process halts. If at least one of these guys is not 0, then you define G1 to be G union with all the non-zero reminders. And then you just repeat the process using G1 instead of G. So you take all possible polynomials from G1, you compute their S polynomials, you reduce them with respect to G1, you get all the reminders. And again, if these guys are 0, then you are done, and G1 is the Grobner basis. If not, then you have to add them and define G2, which is G1 together with all the non-zero reminders. And you proceed in a similar way. So the claim, it's also not obvious claim. This process terminates after finitely many steps. And at the end, and this part is simple, and at the end, you will get a Grobner basis defining exactly the same ideal. So after finding many steps, you will get something like this. So the set on the step number n will be exactly the same as the step number set on the step number n minus 1. So there exists an n with this property, and then Gn is the answer. So let me show you the algorithm again. So there are two different questions. So how does it work and why does it work? So first of all, I want you to understand how it works. So are there any questions regarding the process itself, how it works? Is it clear, or should I explain how it works in more details? Okay, so how it works, it's probably clear. Now, in order to prove that it works, we need to prove several things. First of all, we need to prove that the process halts. So that there is such a number that we have this equality. And if we have this is the hard part, and I'm not going to prove it. Just believe me. Probably if we have enough time at the end of the next lecture, I will prove this.
Excuse me, and can you remind me, please, what is SGIJ?
Oh, this is the S polynomial. So here is the definition. So you take both polynomials. They are presented in this form.
It is like LCM, yeah?
Yeah. You multiply by some monomial and the coefficient to get the LCM of their leading terms, and then you subtract one from another and cancel the leading terms.
Okay, thanks.
No problem. So yeah, you should remember this definition, because the S polynomials play the crucial role in the theory of Grobner basis. So like almost everything can be done using this S polynomial. They take part in all possible criteria, etc., etc. So okay, so the halting problem, I just want to skip.
Will we like ever prove something about?
What again?
Will we like ever prove any of the results we've obtained today?
Well, I want to postpone all the proof for the next lecture.
Okay. Cool.
So now I want to discuss how everything works here, because it's more important to know how things work and how to apply them, because you just need to know the proof why they work just once. But since you know why things work, you will only apply all these tools, and it's better to understand how to apply the tools and what kind of procedures you have in your disposal. Because, well, okay, I can spend like the whole lecture to prove one criterion, and this gives you almost nothing. Yeah, you will know how to prove that everything works fine here, but you won't be able to apply all this stuff.
Yeah, no problem. I just was afraid that we will not prove it at all. If we are going to prove it and some lecture, that's no problem.
I'm sorry, there was some problem with the sound. Could you repeat?
And you was afraid that we would never prove it.
Well, we will prove this criteria. And probably we'll prove this halting problem for the Buchberger algorithm. Okay, so, but, okay, talking about proofs. What I want to prove, I want to explain why why this process gives you a Grobner basis of the ideal. So using the fact that the process terminates, okay? This fact I want to explain. So suppose that we know that the process terminates. Now I want to show you that the process leads you to the required answer. So we have to show, well, first of all, we have to show that the resulting set is finite. Well, this is clear because on each step we get a finite set, so Gn will also be a finite set. So the step number one, the item number one is clear. Now, I want to show you that the resulting set Gn generates exactly the same ideal as the initial set G0. or G capital. Well, in order to prove that, it's enough to show that G and G1 generate exactly the same ideal. Then, using the same argument, we show that G1 and G2 generate the same ideal, etc. And then we will get that G and Gn generate the same ideal. So let's show that G and G1 generate the same ideal. So I want to show you that G and G1 generate exactly the same ideal. Well, let's recall the definition of G1. G1 consists of G and the reminders. Well, since this set is not smaller than this one, I mean, G1 is not smaller than G, it contains G, then it's clear that this ideal belongs to this one, because, well, here we just have more linear combinations. Well, in order to show the other embedding, if we want to show this, we want to show that all the reminders are actually here in this initial ideal. This is one. So if we prove this, then then we obviously have an inclusion in the opposite direction. But let's try to remember the definition of all these reminders. We started from an S polynomial, which is of the form C2T1 Gi minus C1 T2 Gj. This was the definition of this guy. And as we can see, it belongs to the ideal generated by G, because it's a linear combination of Gi and Gj, and they are elements of G capital. Okay, but later we made a couple of steps of elementary reduction. But what does it mean? When we do an elementary reduction with respect to some polynomial, let's say Gk, it means that we replace the initial polynomial by the polynomial of the form because the elementary reduction works like this. We multiply Gk by some monomial and by some coefficient and subtract this expression from the initial polynomial. And after a finite number of steps, we will get the remainder Rij. So it's enough to prove that if this guy was in the ideal, then this guy is also the result of the reduction is also in the ideal. But you see, if this was in the ideal generated by G, then this guy is by definition in the ideal generated by G. And since this is an ideal, the result is also in the ideal. So applying this argument finitely many times, we will prove that Rij also belongs to the ideal generated by G. So we will prove this, and this completes the proof of the other inclusion. So this proves that after that we have this sequence of equalities. So after finitely many steps, we will get this Gn. So the ideal generated by G and Gn is exactly the same. Are there any questions here? Okay. So, and now we just need to show that Gn is the Grobner basis. But let's analyze how the algorithm works. The algorithm works as follows. You take all possible pairs from Gk, you compute S polynomials, you compute their reductions, and if they are not zero, you add these reductions to your set Gk, and you get Gk plus 1, and then you repeat the procedure. So when do you terminate? So you terminate when all the reminders are zero, which means that if you have this equality, it simply means that all S polynomials for for polynomials from Gn minus 1 are reducible to 0 with respect to Gn minus 1. So this is exactly the condition you have to check by the Buchberger criterion. So by the Buchberger criterion, the set Gn minus 1 and then the set Gn is a Grobner basis. So this is why this procedure leads to a Grobner basis of the same ideal. So the only issue here is to prove that the procedure terminates. And I want to postpone the proof until the end of the next lecture. Okay. Are there any questions regarding this algorithm? Okay, so now we're ready to define the reminder rings, the rings of reminders, or quotient rings. Well, again, we have a field. We have this polynomial ring. And I fix a lexicographical order. Now, suppose I have an ideal generated by G1, Gk. So G will be the set of all these guys. Now, using the Buchberger algorithm, we compute G0, the Grobner basis of the ideal I. So we start with G and apply the Buchberger algorithm to G and get G0. And we know that in this case, the ideal I is also generated by the set G0. Now I can define the reminder ring. So I will define f x1 xn quotient by G0. The ring of reminders, or a quotient ring of the polynomial ring by the ideal generated by G0. So in order to define a ring, I have to specify a set and two operations, and I have to check that these operations satisfy the definition of a ring. Well, here we will get even a commutative ring. So, but first of all, I have to specify the set. So the set here consists of all reminders with respect to G0. So as a set, this is the set of all polynomials such that f is a reminder with respect to G0. F is a reminder with respect to G0. So the definition is exactly the same as in case of polynomials in one variable. So when we dealt with polynomials in one variable, we also took all the reminders with respect to a generator of an ideal. But here, we don't have just one generator. We have a lot of generators, and we have to switch bad generators to good ones. And then using these good generators, we define the ring of reminders. Now it's just a set of reminders. So how do operations work? So if you want to add two polynomials, well, it's clear that if you have two polynomials and they are reminders, then the sum of the reminders is a reminder. So this is also a reminder. Because what does it mean to be a reminder? It means that each monomial here is not divisible by leading monomials of elements of G0. Well, if all monomials here are not divisible by leading monomials of G0, and all monomials here are not divisible by the leading monomials of G0, then the sum contains, well, at most, the union of the set of monomials of f and f prime. So there are no monomials divisible by the leading monomials of G0. Then this is a reminder. So the sum here is given by the usual addition of polynomials. And the multiplication is an interesting part. So if you want to multiply polynomials, so you do this procedure. You multiply polynomials using the usual product of polynomials. So this is the usual product of polynomials. This is the product of polynomials. And then you reduce the product with respect to the set G0, and you will get your remainder R. So the result of the multiplication in this ring is this remainder. So if you want to multiply two polynomials, you multiply them as usual polynomials, then reduce with respect to G0, and this is the result. Well, one can show that this will be a commutative ring. So one can show that this guy is a commutative ring. Well, there are several ways to check this. I don't want to waste our time doing that computation, because there is a clever way of doing this. And if you do it in a clever way, this will be obvious. But in order to explain this in a clever way, I have to explain you what is the quotient of a ring by an ideal. I didn't define you this creature, so I don't have a tool in my disposal to prove this in a very simple way. But if you want to do this in a straightforward manner, then it's a computational hell, but it's doable. But I don't think it's worth doing, especially during the lecture. But just believe me, the resulting structure is a commutative ring. Okay. Well, so what would I discuss now? Oh, okay, let's discuss the dependence of this construction on the choice of the Grobner basis and on the choice of the order. So here, everything I defined here was highly dependent on the lexicographical order and the choice of the Grobner basis. Well, it actually happens that the Grobner basis itself doesn't affect the structure. Let me explain what it means exactly. So the remark number one. Well, if you produce two Grobner bases, suppose that you have two different Grobner bases, where G1 and G2 are Grobner bases of the same ideal I as before. Well, Grobner basis is not unique. There are a lot of different Grobner bases, and it could be infinite. But in this case, I just want to discuss finite Grobner bases. So if you have two different Grobner bases of an ideal I, then the remainder is of any polynomial with respect to G1 and G2 will be exactly the same. So for any polynomial f of the polynomial ring, the remainder, let's compute its remainder with respect to G1 and its remainder with respect to G2. Well, the miracle is that these reminders will always be the same. So this always holds. So this happens if you have two Grobner bases, but for exactly the same order. So let me clarify this here. So the order is the same. So the order lex. So I fix some lexicographical order, and I compute at least one, well, two different Grobner bases for these, for the same lexicographical order. And if the order was the same, it doesn't matter if your Grobner bases are different. The remainder you will get with respect to each of the Grobner bases will be exactly the same. So you can use any Grobner basis for a fixed lexicographical order to compute reminders. So this remark, I'm not going to prove it because again, there is a simple way to prove it, but I have to define the quotient ring with respect to an ideal, and without doing this, this is just a computational nightmare. and I believe it's better to deal with ponies than with devils. So let's stick to ponies and rainbows and fairy tales instead of reading some hellish stuff. Okay, so everything here in this construction depends on the choice of the lexicographical order only. So if we fix a lexicographical order, it doesn't matter which Grobner basis we take here, this set will be exactly the same. It doesn't depend on the Grobner basis. Okay, and now I want to discuss what happens if we change the Grobner basis. In this case, this set will be different for different lexicographical orders. Well, it may be different. It may be the same or it may be different. But the resulting rings will be isomorphic. So let me formulate this as a remark number 2. So suppose now, oops, wrong color. Well, suppose now we have 2 different lexicographical orders. So we have lexicographical order 1 and the lexicographical order 2 on the monomials of this polynomial ring. And we have an ideal generated by G1, GK. And using Lex1, we computed a Grobner basis 1. This is a Grobner basis of I. And using the lexicographical order 2, we compute a different Grobner basis. This is a Grobner basis of I with respect to this lexicographical order. Well, in both cases, these 2 sets, G1 and G2, they generate the ideal I. So the ideal I will be generated by G1 and G2. And using these Grobner bases, we can produce the quotient rings as before. Oops. G2. Well, the claim is that these rings are isomorphic. And let me show you the explicit formulas for the isomorphisms. For the isomorphism and its inverse. So if I take a reminder here with respect to G1, then I take it to the reminder of F with respect to G2. So I just recompute the reminder with respect to G2, and I take F to F prime. And in the opposite direction, the map works in a similar way. If I take a reminder with respect to G2, I just recompute the reminder with respect to G1, and I take G to the corresponding reminder. Well, one can show that these maps are inverse to each other isomorphisms. So these maps are isomorphisms between these 2 rings. Okay. Yeah, and again, it's obvious when you know the definition of a quotient ring by an ideal and computational hell if you want to do it in a straightforward manner. Well, it's possible, it's doable, but it just takes a lot of time. Okay, yeah. Now I have like 6 minutes, and I want to cover one additional topic, but just in case, are there any questions regarding what was here? Okay, so we will practice during this seminar how to compute with these strange rings. So the Grobner basis allows you to solve several problems in an effective way. So let me show you these problems. Problem number 1. Suppose you have a polynomial ring and an ideal and a polynomial, and you want to check if this polynomial belongs to the ideal. So how to check this? So the Grosvenor basis gives you the answer. So suppose your ideal is determined by the elements G1, Gk. Then what you do, first of all, you compute the Grosvenor basis. Oh, no, first of all, you fix lexicographical order. Fix lexicographical order. Because if you want to apply Grosvenor basis, the first thing you have to do is to fix an order. Now, since you have an order, you compute a Grosvenor basis of the ideal I. You compute G0, a Grosvenor basis of I. You just apply the Buchberger algorithm to the set G1, Gk. And then, after that, you compute the remainder of F with respect to G0. And here you have two options. It's either 0 or not. Well, if it's 0, then it simply means that F belongs to I. And if it's not 0, it means that F is not an I. Well, it should be noted that you cannot use this procedure, this decision rule, if G0 is not a Grosvenor basis. Well, if you reduce a polynomial with respect to a set of polynomials and the result is 0, then F belongs to the ideal. But it may happen that F belongs to the ideal and the remainder is not 0 in case G0 is not a Grosvenor basis. So in order this to be a criterion, a well-defined rule, you have to use a Grosvenor basis here and not just a random set of generators. So this is what's called a membership problem, how to check if a polynomial belongs to an ideal. Are there any questions? Okay, and I will formulate just one additional problem. So a problem 2 is eliminating variables problem. It's used in order to solve any polynomial equations. So there is a method of solving polynomial equations. It's analogous to the Gaussian elimination. So let me explain the main ingredient of this method. So suppose you have a polynomial ring and you divide all the variables into groups. And you have an ideal here, and this ideal is defined by a set of polynomials G1, Gk, and you want to compute the intersection of this ideal with the subring of polynomials depending on x1, xk only. So this means that you want to take all the polynomials from the ideal I depending on x1, xk only. Well, this is exactly the elimination problem where you want to eliminate all these variables with high index. Well, how to solve this problem? So what you do, first of all, you choose a lexicographical order with the following property. You want the variables x1, xk to be strictly smaller than xk plus 1, xn. The order here doesn't matter. The order here is any order you wish. But each variable here must be strictly larger than each variable here. After that, you compute the Grosvenor basis of I with respect to this order. And then, on the third step, you take G to be all polynomials from G0 such that G depends on x1, xk only. Depends on x1, xk only. So you take all the polynomials from the Grosvenor basis depending on this set of variables x1, xk. Then the claim is that the intersection is generated by this set G. This is how to apply the elimination process. We will use it to compute an image of a curve. I'll show you during the seminar how it works. Okay, now this is the end of the lecture. We have like literally 0 minutes left. So if you have any questions, please ask. If not, then see you next time, and thanks for being here.
Thank you.
Okay, thank you guys.